have a uniform 2 kilogram circular disc with radius 20 centimeters. It's rotating clockwise about an axis through its center with an angular speed of 30 revolutions per second. The second disc, 1.5 kilograms and radius of 15 centimeters, it's not rotating, but it's dropped onto the first disc so that the axis of rotation of the first disc passes through the center of the second disc. So their centers are the same. Because of friction between the two discs, they'll eventually end up rotating at the same rate. Okay? We want to know what is the final angular speed of the two discs when they are rotating together. So this is a collision. Collision momentum. In this case, since we're dealing with rotating objects, we want to look at angular momentum. So initial angular momentum of the system consists of the two discs, has to equal the final angular momentum of the system. So initially, we have two separate objects. They're not moving together. So we have the angular momentum of disc 1. So that would be its moment of inertia. I'll call this M1, this R1, this omega 1, this M2, this R2. So angular momentum, moment of inertia times angular speed. So I1 plus omega 1, or sorry, times omega 1 plus I2 omega 2. That's the initial angular momentum of the system. But what's omega 2? 0. So that whole term goes to 0. Finally, they're stuck together, they're rotating as one object. So we're going to have the sum of their moments of inertia. Remember, you can't simply add their masses. You need to add their moments of inertia. So the total moment of inertia times the final angular speed. So we said these are circular discs. Looking off the table in the book, the moment of inertia for a circular disc is 1/2 mr squared. So I1 will be 1/2 m1 r1. I2 will be 1/2 m2 r2 squared. So we know m1 is 2 kilograms, r1 is 20 centimeters, omega 1 is the 30 revolutions per second, m2 is the 1.5 kilograms, r2 is the 15 centimeters. Plugging and chugging through there, the final angular speed ends up being 21 revolutions per second. So the units on our final angular speed are the same as our units on the initial angular speed. Since we had the initial angular speed in revolutions per second, our final angular speed is also in revolutions per second. Questions? Energy. We haven't talked about the equation yet for energy. But because they're moving, because they're rotating, they will have kinetic energy. But the energy will not be conserved in terms of potential and kinetic energy in this collision. Turns out the energy always changes. It goes into other forms. There's friction between the plates that causes them to finally move together. So there's energy turned into heat.